In this class, we are going to introduce stoichiometry and tie the energetics with stoichiometry. We have covered the stepwise energy flow during the catabolic reactions and anabolic reactions, and the role of electron and energy carriers like NADH and ATP. We have touched on using half reactions to calculate the overall free energy. We will take a closer look at the half reaction approach to determine the stoichiometry of the biochemical reactions. Stoichiometry looks at the molar and mass ratio in a chemical or biochemical reaction, which is closely tied to the energy flow. This graph shows the energy flow for cell synthesis when the electron donor is broken down. In reality, the electron and energy carriers like NADH and ATP generated during catabolic redox reaction from the electron donor is used for anabolic cell synthesis. This can be simplified to a fraction of the electron from the electron donor is transferred to the electron acceptor to provide energy for converting the other fraction of electrons from the electron donor into microbial cells. We can use the half reaction approach to describe this process and analyze the energy flow. Half reactions for electron donation, electron acceptance, and cell synthesis can be written differently for different electron donors, electron acceptors, and nitrogen source. This gives a lot of flexibility as there are many combinations for the diverse biochemical reactions. The half reactions can be looked up in tables 5.3, 5.4, and 5.5 in the RM book. For the energy reaction RE, the electron donor donates electrons to electron acceptor to generate energy. The electron donation half reaction RD is combined with the electron acceptance half reaction RA. The left and right side of the RD in the table needs to be flipped before combining with RA, hence the negative sign for RD. As an example, let's find out the energy equation for the denitrification process using benzoate as carbon source. Because it is denitrification, nitrate is used as the electron acceptor. Benzoate as the carbon source is the electron donor. Make sure that the electrons are in the right place. If not, flip the equations. Simply add these together and cancel out the water and proton occur on both sides of the equation. We can also compute the delta G value at the standard condition of the reaction by adding the delta G for electron acceptance reaction and electron donation reaction. Please note the negative sign for delta G of RD because the half reaction is flipped. In the cell synthesis reaction RS, the electron donor combines with the nitrogen source to form cell material. It is the combination of the same electron donation half reaction, RD, and the cell synthesis half reaction, RC, with appropriate nitrogen source. We can continue our example for the benzoate utilizing denitrification bacteria. It uses ammonia as nitrogen source for cell synthesis. We can find the cell synthesis half reaction that uses ammonia as nitrogen source. The electron donation equation stays the same. And combine these together gets the overall cell synthesis reaction. After knowing the energy reaction RE and the synthesis reaction RS, we can put together the overall reaction by introducing the fractions. The fractions of electron transferring from electron donor to electron acceptor to generate energy, Fe, and the fraction of electron transfer from electron donor for cell synthesis, Fs. Because the sum of Fe and Fs is 1, the overall reaction can be written as this. The superscript 0 on Fe and Fs indicates that they are the fractions for an ideal condition when the substrate is not a limiting factor and all the energy are used for self-synthesis, not for maintenance. Let's continue with the previous example. We can look at the overall reaction of the denitrification bacteria using benzoate as carbon source and ammonia as nitrogen source to grow. We can assume that 60% of the electron is used for energy and 40% of electron is used for growth. So Fe is 0.6 and Fs is 0.4. We can multiply Re by Fe and multiply Rs by Fs, then simply combine these two components together. Here we look at a more familiar example. Aerobic oxidation of glucose using ammonia as nitrogen source. If you want to work on this yourself, you can pause this video now. So now we can write the half reactions for electron donation and acceptance and combine them into energy reaction Re. We then write the half reaction for cell synthesis and combine it with electron donation half reaction to get Rs. Let's assume that 60% of the electron is used for energy and 40% of the electron is used for synthesis. So Fe equals 0.6, Fs equals 0.4. So we multiply energy reaction by 0.6 and multiply cell synthesis reaction by 0.4 and combine them to get the overall reaction, which is normalized to 1 mole of glucose. This reaction is in molar ratio, and we can convert it to COD ratio by converting each component to COD values. 1 gram of COD equivalent of glucose can generate 0.4 grams of COD equivalent of biomass. The true yield is the cell growth in COD per unit of substrate consumed, also in COD. And it is 0.4 for the previous example. When ammonia is used as the nitrogen source, the true yield equals Fs 0, as there is no change in the oxidation state of nitrogen. All electrons donated are used to convert CO2 to biomass. But when nitrate is used as the nitrogen source, a part of the electron donated are used to reduce the nitrate to nitrogen with a +3 oxidation state. The true yield will be lower than Fs0.